yours.
Thank you, Deng Sing. And yes, the timing is good because it's already night in Europe. And yes, I wanted to focus in my presentation about, to some extent, specific challenges of low light and nighttime vision, which is certainly full of dark swans or black swans, as they were called before. Um, and let me see if I can up. Does it work? Yes. So the the I'd like to discuss this issue of or these challenges in the context not only of autonomous driving but also of assisted driving, so advanced driving assistance systems that are already in commercial cars, because there is a continuum between these two types of systems. So why would there are so many people in the industry and the academia working towards this goal? Of course, because with the help of also electrification and connectivity, there is really the hope that this will one day make transportation and mobility, well, safer, first of all, but also more efficient and more inclusive, so really better transport for people and goods. So that's great, but as we also saw in the previous talk, we are not yet there, and it's extremely challenging at large. And the main reason being that we have this AI system, which is obviously safety critical, which has to run in real time on a budget in a car and in the wild, and on top of that, it has to be there for 10 to 20 years. So I guess we have a concentrate of maybe all the possible challenges when it comes to artificial intelligence. Um, so maybe I have the Zoom thing on my screen, which block my view. So uh, so if we really want to have one day this type of systems on the road, we really have to address not only the black swans, but also just the massive variety of all the operational domains. And even low speed maneuver for parking can be very challenging. So it's for all the type of driving, all the types of environments, from parking lots, and all the way to highway and busy streets in cities. Of course, it's for all the regions in the world, and because it's the focus of this workshop, it has also to work in all weather and light conditions. In order to achieve that, there are many things which can be done. There some that were just mentioned before: data augmentation and data synthesis, but also all sorts of adaptation. This is in terms of modeling and data. In terms of system themselves, it's probably good to leverage the complementary of different sensors, and this is very often done with cameras, lidar, radars, also ultrasonics for low speed maneuver, and also microphones in some cases. Um, Also, it might be interesting to have multiple models for the same function, so algorithmic redundancy, and being able already to estimate or to predict the confidence in a prediction would already be something very helpful, in particular if you can hand over to a human driver. And last but not least, probably especially for the the long tail scenario and all the very rare cases, having some knowledge of the world would be very helpful. But as we all know, it's not very easy to get. Um, so let's talk about real data for a moment. Um, the thing is that for these perception stacks that we have, they all rely on machine learning, deep learning in particular, and the state of the art mostly rely on fully supervised learning, in which not only you need to have large quantities of quality data with a good coverage, which is already very difficult to get, very expensive, sometimes dangerous. And on top of that, you need to annotate very, again, with quality and at scale, which is and it's done very often by human annotators, and it's extremely tedious, time consuming, expensive, and sometimes even extremely difficult for a human being. So just taking examples for night time scenes. So this is an example from the dark Zurich data set where you have semantic segmentation. So you can imagine how much time it takes to annotate that already for daytime image. And actually, in this case, and Deng Xing can confirm later, it uses actually annotation of daytime images, but it's extremely time consuming, of course. Likewise, if you want to annotate either 2D and even worse, 3D bounding boxes in images, very complicated, especially at night when the visibility is low. And the last example, which is actually an in-house example at Valeo, where we have a fisheye cameras front and back here, and we want to, well, we use that at night or also indoors. And in this case, we want to annotate the dirt on the lens. And at night, it's very hard for the human annotator to distinguish between the dirt and an actual object in the scene at night. Just another example that I found interesting to show. And in any case, no matter how much effort and energy and time we spend there, I would argue that it will always be insufficient because of the impossibility to cover everything with real data. Uh, but nonetheless, the good news is that for autonomous driving, there has been quite some effort in the last 15 years or so in the community, and there are really now a wide range of data sets. So this list is not exhaustive. Probably they are the most well-known ones, and there are already 20 on this slide, including half of them just in the past 2 years, less than 2 years. So that's and they all have images, and most of them now have also lidar, point clouds, etc. So multiple sensors and all sorts of annotations in 2D, in 3D, etc. So that's great. But if I switch off the light and I look at the nighttime data, well, there are not so many of them with night scenes, and most of them in this slide here have only a small fraction of their data at night, except for dark Zurich, because it's one of the key point of the data set. And also, so we have real data annotated at night, but probably much less than for the rest of the type of scenes. So just going through some examples I found interesting. So this is from the Oxford robot car data sets, where they, I think over 1 year, they did 100 times the same circuit in Oxford. And so and it's roughly aligned, so that's good. And you see on the right at the same position over the 100 passes, and you see that there are probably 9 of them which are at night, and you see 4 of them blowed up on the right. And it gives a sense of how difficult it is with all the glare, the reflections, etc. And sometimes exactly at the same location, Oxford, it can be very diverse even in terms of lighting. I found that interesting. I'm not sure, by the way, I don't remember exactly what annotation they have apart from the localization. Initially, it was a data set for localization or relocalization. This is from Berkeley Deep Drive 100K videos. And on this one, there are quite unusual type of annotations alongside semantic segmentation. They have road marking and lanes which are annotated, which are very interesting, and also drivable areas, etc., plus the usual suspects with bounding boxes. But I think these are videos, which is also interesting. And this is from I'm sorry again, the title of my, oh, there we go, I can move down the thing. So this is from Dark Zurich. Like in the Oxford robot car, there is a rough localization between images, so you have roughly aligned views of the same places or same localizations in Zurich at day and night, which is very useful to transfer annotation. And as a matter of fact, I already showed that, but the annotation in this case is semantic segmentation. So these are 3 examples from this data set. Um, um, Last examples are from on the left from new scenes, where they have these 3D bounding boxes in night images, and on the right, these are just videos, I think, yes, from Waymo Open data set. I don't remember the exact extent of the annotation they have, but for sure 3D bounding boxes, but I believe some other types of annotations. Right, so that's great. We have already that, like 10 data sets with some nighttime images. And if we look as well at pedestrians and vulnerable road users, which is a class of road users which is very important to look at, especially at night, because they are even less visible at night and more vulnerable, as it were. So for this very specific type of objects, so to speak, in the scenes, there are specific or specialized data sets. Like I have listed this, there are 10 or so here. And in this case, if we look at the night part, it's even worse. So there are only 2 of them where there are nighttime scenes. I think I did check recently, so maybe there are some mistakes here, but roughly just 2 of them. Night owls is specifically dedicated to nighttime, so it's all of it. And for EuroCity, it's probably 1/5 or 1/4, which is nighttime. And this is an example from night owls, and you see that it's about pedestrians, cyclists, and motorcyclists, and riders of bicycles. So it's a very interesting data set. In any case, so this is if you these are all these data are useful if you want to do supervised learning for your favorite perception tasks at night. But because it might not be sufficient, there are all sorts of things that you can throw at it, alternative supervision to improve the performance of your system. I'm not going to at all to go through this list, and in the remaining time, I will essentially focus with some examples in my team where we do look at domain adaptation and also augmenting data with a GAN. So domain adaptation. So domain adaptation, in particular, unsupervised domain adaptation, is this type of setup where you do have annotated data in a source domain, and at runtime you have actually another type of domain, which is the target domain, for which you might have examples but unannotated. So the typical setup for nighttime vision would be that you have loads of annotated daytime images. So daytime is the source domain, and you have some examples, maybe even many examples from nighttime images, but without annotation. And you want to leverage both at train time to do as well as possible at runtime on your nighttime images. So one thing that I'd like to mention which is complementary to other techniques in unsupervised domain adaptation is the thing that we've been pushing since 2019 with this work at CVPR called Advent. So it's an adversarial domain adaptation technique. So there are which is a subfield, as it were, of domain adaptation, and in which we look at how to align the target and source distributions, not so much at the input of the model, but close to the output. And using an adversarial learning where there is a classifier, as we will see, which helps. So the idea is that we want to, so we have a model, a perception model that we want to train. So we have annotated source data examples for which we can so learn the classic way with a supervised loss, but it's not the target domain here. So what we propose is to look at the actually at the predictive entropy of the predictor, which is so looking at essentially the logits of the model, and using now unannotated target examples, we can look at this predictive entropy and have first of all a discriminator in charge of trying to decide whether this entropy stems from source or target data. In this way, it will force the main model to become less and less uncertain on the target data. And also we have an explicit loss to minimize this entropy. And so it's a fairly generic mechanism which can be used for different tasks, like in particular semantic segmentation or detection. Another thing that and at test time, of course, you just have target domain new examples to look at. Another interesting tool that we used coming from semi-supervised learning is safe training or pseudo labeling, where you use the first version of your model then to do auto labeling of your unannotated target domain images. And these examples, there are some of these annotations are probably less good or more noisy, so you need to find a way with some confidence criteria to exclude them. So if you have that, then you can have a small set of fairly confident pseudo labels on which you can do supervised learning for the next version of your model, and this quite systematically boosts the performance. So it turns out that this system was not at least is not state of the art for the day to night domain gap, as actually was showed by in some of the recent works by Dexing. But I wanted nonetheless to show an example for detection in bad weather, not nighttime, but foggy time. So this example here is is just two scenes of two views of the Cityscapes foggy dataset, which is Cityscape with synthetic fog, incorporated using the depth in the scene. And if you run your an SSD object detector, which has been trained only on the clear time images, this is what you get. Actually, nothing on the left. He missed everything, and only the most obvious cars on the right. And then if you do the type of domain adaptation that we proposed in Advent, then you can recover way more. And this also translates in the numbers in the table below, and you see the MAPs in the MAPs in the per classes, and also the mean average precision over the classes. So there is quite a good boost in performance. Of course, there is quite some margin for improvement, but it's interesting to see how this adversarial entropy-based adaptation can already help or contribute narrowing down the gap between source and target. Another interesting thing that you can do for domain adaptation, if to leverage, if you have that, to leverage multiple modalities. In that case, we looked at cameras and lidars, so the inputs can be either monocular image or a point cloud. And the task that we addressed is the semantic segmentation of the point cloud. So we want to produce semantic classification of each of the point in the point cloud. So you can do that either with a 2D input or the 3D input itself. And the idea is to exploit the complementarity between the two modalities in order to do domain adaptation. So you have two models, one which can for each of the stream or for each of the input modality, and they are going to sort of teach each other in a cross way. So it's cross modality learning, and we put that into unsupervised domain adaptation framework. So into more detail, I won't give too much detail, but you see that on the source domain, you have both images, point clouds, and the ground truth, but it's in this case, it's daytime. So this is the annotated source domain. And on this one, we can train both the 2D model and the 3D model with full supervision. On the target domain, which is nighttime here, we only have the raw data, images, and the 3D point cloud, but no annotation. And so we have different losses. One is supervised on the source domain data, and for the and the other losses, there are two of them important: the XM, the cross-model losses, which is this sort of cross teaching between the two modalities. So each one is trying to there is actually an actual knowledge distillation between the two with the classic knowledge distillation tools. On top of that, we have pseudo labeling, something that I mentioned before. So just to show examples here, you see that on the left, if you don't have, if you do domain adaptation, but without leveraging the cross modality. You have a number of errors or things which are not detected, so either misdetections or so either false positives or false negatives. And by doing this cross model UDA, we get some improvement. In this example, you see that typically on the if you want to do the 3D semantic segmentation from the 2D image, without the cross-modal learning, you would not get the car that you see from front on the right with the headlamps, and you recover it on the right. So we have this way number of improvement, and it does translate into numbers. So in this experiment, we used the new scene for which you have day and night. So it proved very useful. And so the numbers you see are for the two, so we can evaluate the performance of the 3D semantic segmentation from either the image or the point cloud. So it's 2D or 3D. And you see here, so the baseline is when you train only on daytime, so on supervised learning on the source domain data. The oracle is the case where you actually have annotation in the target domain and you do fully supervised learning. And in between, you see either the adaptation without cross modality, which is UDA, and then the proposed method, which again bring 2 more points or 3 more points of mean IOU in performance. And again, an example where again a car coming the other way with the headlamps on is recovered thanks to this cross-modal adaptation. And the last, the second work or piece of work I wanted to mention is this work in collaboration with colleagues at the Czech Technical University in Prague, which we call artificial dummies. So a dummy is in fact what you see on the right. These human-sized doors which are used for the on the test tracks to test in this case an emergency braking system. And by analogy, now we are going to have these fake humans, but in the images which are going to be generated. And the rationale here is that especially for pedestrians, in the data we have, the real data we have recorded, annotated, etc., there is quite a lack of diversity of various poses, maybe rare poses of people lying or doing crazy things, etc. And the same with the appearance. So the idea is to really try and leverage the power of a conditional GAN in order to generate, to create and insert new characters in the scenes while controlling the pose and the appearance. And hence doing some data augmentation. And in this work, we use that for training new models, but it could be also used for validation and testing and searching corner cases. So the system is, again, I'm not going to detail, but roughly what you can provide either manually or automatically is one example of a real person, which gives you the appearance, like the clothing, the piece of image of scene in which you want to include this person, so an image patch, and the pose, which is specified with 2D joints, which actually can be generated from a learned distribution of 2D joints. And then with the conditional GAN that we built, you can generate in place a new human in the scene. And you see examples in the middle part, and using that, then you can train on this augmented data. And in this case here, you see that all the green detections have been recovered thanks to the retraining of the detector with this augmented data. And these are examples of scenes. So in each of these single scenes, actually, there is also bad weather on the top right, where there is snow, and some night at the bottom right as well. So there are always at least one fake human. In the case that there is a single one, it's easy to spot, but maybe it's a bit harder in the other scenes. Um, And at night, it does translate into numbers. So what we showed it, if you, in particular on night holes, if you train, I'm not going to go into the numbers. I see that Daniel is already ready. If you augment, if you train only on daytime and you have night images without any pedestrians ever annotated, already with fake pedestrians that you include in these nighttime scenes, you can already improve quite a lot the detection. And this is just to show one of these fake human. Interestingly enough, this one is naked foot. Probably not very realistic, but it turns out that realism is maybe not the end of the story. It's how useful is the data per se. And the last thing I wanted to mention is really the last thing promised is also you might want to translate your images in order to go from, say, daytime into nighttime. And thus leveraging existing annotations. So there have been, following all this style transfer trend, there has been the attempts. So these are attempts using CycleGAN. I haven't put the references here, at least on my slide here, I can see them. And you see that it's not quite right, because it's not only about texture. And this is another example from another work, and I will skip that just to show you my last image. It's an ongoing work, so I won't tell much about it, but the idea is that we try to explicitly, you will see in a second, put lights in a scene as at night, but leveraging a knowledge of the 3D of the scene. And this is what we are able to get at the moment. And on this sneak preview, I will stop here with some takeaways. We definitely lack, we don't have enough real data for this specific nighttime and low light scenario. There are ways to improve on the performance of the perception, including with multiple sensors, some domain transfer, some simulation, etc. And on a side note, we also need to look at the drivers at the same time, especially at night where they are sleeping. And there are probably synergies to be found between exterior and interior monitoring, in particular at night. And this is the end of my presentation, and thanks to all my team, which is on this slide. Thank you very much.
Yeah, thanks a lot. Thanks a lot for the very impressive presentation, Patrick. So are there any questions from the audience? I think we can take a few questions here. Yeah, is there any?
There are some questions in
Yes, go ahead, Christos, you can read the question.
Yes, cool. So Adam asks if you find the models learning hidden artifacts, pixel distribution patterns present in GAN generated data, specifically in fake humans, and whether the generative model considers variance in height and color, for example, clothing.
I'm not completely sure about the question. Our attempt, it was really to be able to control by example. So actually we use real appearance of real other pedestrians in, say, at daytime, and we transfer that. So at least we visually we managed to get sort of a good blending with the new illumination. Probably there are, I mean, when you look carefully at the augmentation, there are plenty of artifacts, and actually the detector might pick them up, which is not a good news. But if usually you don't learn only on these examples, it's in order to augment, so this mitigate the risk. And by the way, there is a similar issue with anonymization. When you replace all these data sets, they are anonymized either by blurring the face, or now we do that in our recently released data set Woodscape. We replace the faces by fake one using a GAN. So the risk is always, there is always this risk, or this fear of, or maybe there are very specific artifacts which can be picked up by a model trained on that. We haven't seen that, to be honest, but it's something really to take into account when designing these systems and leveraging this augmented data.
Mm-hmm. And there is like another question, but I think we can skip that because it's more specific.
Okay.
Yeah, if you have question, you can also unmute yourself, then ask directly
in the chat.
Yeah, maybe I can also add one question here.
Go ahead.
Yeah, it's really great to see you summarize all this nighttime data set, the challenge. I mean, although it's we have, let's say, relatively limited results compared to daytime, but still there are multiple data sets for different tasks are presented there. So do you see any chance that we can learn from all these different type of data sets, some of them for potential detection, some for semantic segmentation? Is there any way that we can somehow learn jointly from all this partial data set to actually to address nighttime semantic understanding in general?
And not only for nighttime, but in general, I think when you see all these lists indeed of data set, there are overlap and differences and complementarities. Really, the we feel like we should use all of them, but there are also I'm a big believer into cross or multi data set learning and testing. So it can take different forms. It comes with specific challenges between how do you balance things in the mini batch, for instance, between different data sets, and they come with different annotations. So I think they could be using them collectively is certainly promising for self-supervised learning and then pre-training, and also for specific problems like multi-source and or multi-target domain adaptation, which I think would be interesting to do more systematically. There are a few works on that, but definitely something to try out now in order to leverage this this expanding wealth of new data sets, and in particular for nighttime, but not only.
Yeah.
Perhaps I have a short comment. I saw your last slide about this geometry-aware nighttime generation, and actually, I'm very interested in that. So I am curious to see what comes out of this new
very preliminary results. I will be happy to share when they they are consolidated.
Cool. And there is another question
more
from
question. Yeah, go ahead, Christoph. Yeah.
So there's a question from Sabik regarding the comparison with the generated pedestrians. So the question is whether you have a better result when you don't have any real image or pedestrian compared to where you have both synthetic simulated ones and real ones. I guess like
there are many. We tried many different things in this AAAI paper, so to be checked in detail. But overall, it's better nonetheless to have true examples as well.
Mm-hmm.
And maybe for one of the reasons being that, as I said, maybe there is a bit of a spurious correlation with some of the artifacts. Otherwise, not sure about that. But definitely, the empirical finding is that it's good to have also real examples in the.
But perhaps it's not an issue because you actually the numbers are coming from the real test set, I guess. So, or is it not true?
Yeah. Sure. You mean the performance?
Yes, exactly. The performance.
No, you're right. That's true. That's a good point.
So were those numbers then error numbers and error rates instead of accuracy numbers? I might have just.
They were two different. For detection, it was the classic log average miss rate, and for classification, it was. I think it was only miss rate or average precision. I'm not sure, but there are different.
These were MAPs or something, and I was wondering how they were going down when you were adding.
Yeah. It's. I will share the slides, by the way. Sorry, it was a bit fast on this one.